Okay, in this lecture too, we want to understand the notion of a limit of a function. So last time we looked at instantaneous rates of change, or the slope of the tangent line to a curve. And the way we found that was to look at a bunch of average rates of change. So what we did was we had some function, call it f, and then we looked at the average rate of change of this function on some interval from a to a plus h. And then the way that we found the instantaneous rate of change, or the tangent line, was to move this endpoint a plus h closer and closer to a. So in order to find the tangent line at the point a, we look at average rates of change and move this endpoint closer to this endpoint. So in other words, to move a plus h closer to a, we are really moving h closer and closer to 0. So as I do that, right, as you move h closer to 0, so now maybe that puts a plus h closer, and then you look at the average rate of change. So now you get this secant line, and then you move a plus h a little closer, so now you look at the average rate of change between these 2 points, and you get closer and closer to the desired tangent line. So what do we mean by make h close to 0? And what happens to this difference quotient? What happens to this thing? What happens to this thing as h gets closer and closer to 0? So you know we cannot plug 0 in for h, but we would like to see what happens to this function when h is very, very close to 0. So that's the whole reason why we need to talk about limits. So as x gets close to some number c, what does the y value get close to? That's the question. Okay, let's go ahead and give the definition of the limit. And we want to make sure that we're really clear on a subtlety between the notion of limit and value. So here's what limit means. So we will write down this symbol, and here's how you read it. It's the limit as x approaches a of the function f is equal to L. So again, the limit as x approaches a of the function f is equal to L. So we will write that down. We will write these symbols down if the y value of the graph of f gets close to L as the x value gets closer and closer to a. So here's a picture of that. And again, we must get close to one single y value as x gets close to a. And this is a two-sided thing, so we'll break this up into left and right hand in a minute. But as x gets close to a, so for example, if I take an x here and then plug it into the function, so here's f of x. You can see the distance between f of x and L is very small because the distance from x to a is very small. Had I chosen my x on the other side, again, here's some x value, plug it into the function. In this case, f of x is here. Once again, when x is close to a, f of x is close to the value L. So again, this does not say that f of a is equal to L. That's not true. According to this picture, f of a is equal to this number m. So the value of the function is f of a is equal to m. The limit of the function is this different number L. So again, the takeaway from this, the upshot, if you like, is that limit means what y value do we get close to. Value is what is the actual y value. So again, there's a difference between the actual y value and the limit. So how do we compute limits? So we want to look at two methods to start. We'll look at graphical evaluation of limits, and we will look at numerical evaluation of limits.